click this, and you have to click
on this. I say then stop.
Leave studio button.
When I get out, they cannot see me.
Click no, and you have to click leave studio.
From which one? Which one? On this I say leave studio.
This one. This one.
Okay.
Leave studio. You can
Hello? Get out. They cannot see me.
click no, and you have to click leave studio.
From which one? What's going on? This I say for the music. Hello?
Okay.
Sorry for the mix-up. Well, I still hear all the music.
Click no, and you have to click leave studio.
I think that's their problem. For the music. Hello? Yeah. Car? Sorry for the mix-up. Well, I still hear all the music. No, I see. Hello? Yeah. Okay. Sorry for the mix-up. Well, I still hear all the music. Close. Hello? Yeah. Okay. Sorry for the
Hello, Steven, can you hear me? Can you hear me?
hear you.
Yes, I think you have the underline side open because I can hear the music in the background, but we can hear you.
What? That's okay. There's something I should
okay. Hello, Steven. Yes, you see, there's an echo. There's an echo of the same thing being replayed. You must have another tab or window open, or can you check? The same thing being replayed because I can hear my voice on the background. Maybe window open, or if you check, do you have a headset?
Close all this.
The same thing being replayed because I can hear my voice on the background. Maybe window open, or you see, I can hear repeated. The audio is being repeated. The background. Maybe window open, or do you have the underline side open?
Yeah, you can see me. You can talk me.
Hello, everybody. Okay, sorry for all the problem. Now we have fixed the technical problem. We can start the session. I'm Steve Yao, chair of this keynote session. Of course, my duty is to moderate the session and introduce the speaker as well as coordinate the discussion. Today, we are going to have a very exciting topic and a very timely topic due to the current technology in the future trend in the service computing. And the speaker today is very well known in smart manufacturing field. and he had won a lot of honors and awards, recognitions. And let me, I know Jay Lee for a long time, about more than 30 years. And first time I met him, he was at a National Science Foundation, a program director for the industry university collaborative research center program. And at that time, I was at the University Florida. We had a joint center with Purdue University in software engineering for that NSF sponsored center. And that's the first time I met him. But after that, we met in various locations. Well, let me introduce him. His early career, of course, he worked for the National Science Foundation. He also worked in industry, joined the McKinsey and Company, well-known industry consulting company. And then later on, joined the United Technology Research Center, played various leadership role, director in various areas. And then he joined the academic community and university. Currently, he's at the University Cincinnati. He is a very well-known professor, Ohio eminent scholar, and Scott Arthur Chair Professor at the University Cincinnati. I understand currently he's on leave from the university, and as the vice chairman of the board, as well as a member of the board of Foxconn Technology Group, a very large international technology group in the manufacturing of semiconductor area and other area as well. Currently, he's in Taiwan for business, and we appreciate his contribute his all the experience and the good things he can tell us about the applied industry, artificial intelligence for the smart tech manufacturing. And let's listen to his talk, and we should have about 20 minutes for this question and answering. Okay, Jake, will you get started?
Can you hear me?
Yeah, very well.
Okay, thank you very much. Well, thanks for introduction, and I want to thank the organizer for inviting me to speak to this very special conference. So the topic I'm going to share with you is about smart service, but I add maintenance transformation, because the industry and many companies sell maintenance as a service. Of course, later on, they become a value added creation and beyond maintenance. So I think I'll share the topic with you, and we'll discuss some issues and also some research challenges. The outline first, I'd like to give an overview what are trends of a smart service transformation for the last 2 decades, 2.5 or 3 decades. I think people have heard about it, have seen something, but there's some reasons behind it, right? And second of all, I'd like to introduce the industrial AI. This AI, everyone knows AI has been over several decades, but industrial AI, which we focus on systematic discipline. AI is a cognitive science. Honestly speaking, we all develop algorithms by trying and error, but can someone repeat that success using the same data sets with the same success? It's very challenging. So therefore, the industrial AI should be a systematic approach, allow engineers can realize industrial intelligence in a systematic way. Of course, the purpose that the industrial system can be resilient, right? Not just smart. But now give some examples, especially for those large scale and complex systems. I'm not talking about one machine. I'm talking about hundreds of machines, thousands of machines, like jet engines, wind turbines, high-speed train, right? Oil field, so you name it. So eventually, we need to move on to the next. What's the next generation smart maintenance services should look like in 10 years, 20 years from now? Let me give you a few overview, the background, how this started. As Steve introduced earlier, I worked at the National Science Foundation from 91 to 98. In 95, I had an opportunity to work in Japan as a science and technology fellow of the STA at MITI for some research. So at that time, we experienced using the internet as a function to connect machines remotely, right? So eventually, that was the first time actually, because if you look back in 1995, and very few people have cell phone. Even you have cell phone, you cannot connect to the internet, right? Even the year 2000. So basically, we look at the future. You cannot transmit data completely from remote site. You have to use a data model from the remote site and using physical model from the base site. Eventually, connect two together. So this is a very first thing. Then 95. So that was 98 when I joined United Technologies, and I published a paper called Teleservice in Manufacturing. It was the early fellow. So when the year 2000, when I became professor, I had the vision saying one day when product can connect to some kind of network, of course, beyond tether-free, wireless, but the internet. When you have lots of data from machine, what will you do? Assume that, right? Year 2000. So therefore, when data is historical data, sensor data, they will connect it. What can we do? So first, we have to clean the data from the local side, from the edge side, from the product side, and only streamline it, and then correlate them. So eventually, we say, oh, we have to embed something from in a machine. We use a term called Watchdog Agent. It's the platform algorithms, right? It's a machine feature. So you can take the feature like a blood. Human being, we have a blood. Nurse take a blood to test your blood. But what is a machine's blood? It's data. So we take the data from the machine like blood, and we do a test. Like human being, we do cholesterol test, hepatitis B test. So same thing, we can do a data test, same thing. Then you have to do a train model, called decision model, based on the data model from remote site, and also the physical model from the local. Eventually, you compare them. Then you can create a just-in-time service because you know the system degrading. Then you can continuously predict that. You can almost achieve near zero downtime, we call ZDT, right? Of course, the most valuable things you bring back to the information to redesign. Then you can improve design. See, that was the vision of a center intelligent maintenance system we built NSF IUCRC in year 2001. Of course, the first company was excited was Intel, right? Intel marched in, and Ford Motor, United Technology, and etc. So we had over 100 company members over the last 20 years. And in 2018, we had the first called this, the Industry AI Centers planning meeting hosted by IBM Watson in upstate New York. So this meeting brought together all the industry together, look at what's next beyond just maintenance and service. Of course, IBM's well known pushing for services. Obviously, that's what their genesis and is. So we start that. And so for the last several years, just give you a quick overview. I have been on leave from University of Cincinnati to serve as a vice chairman for Foxconn. And Foxconn is a EMS company, electronic manufacturing company. It's ranked number 22 in global Fortune 500. But the key core competency of companies is precision and high volume manufacturing, like your mobile phone, right? Your iPhone and your MacBook and iWatch and Apple Watch, etc. Then you have now, we're going beyond that. We are making an EV, industrial AI, to make our manufacturing smarter. And we have received a number of awards, the Economic Forum and Lighthouse Factory. But I think the current board members, we are pushing for the several new areas. One is the EV platform, and we have launched a number of EV sites globally. will be making EV in the United States as well, and everywhere. Digital health and also endless robotics platform. Of course, the key technology, AI, semiconductor, and 5G, 6G. Recently, company has acquired several semiconductor-related foundries and also the collaboration to make the SI silicon carbide and a modules for the future EV as well. We call 3+3. So with that introduction, let's look at what today I will be sharing with you. First, let's look at the trends of a smart service. Well, typically, when we as engineers, as a researcher, we look at problems, eventually take years, then we gain our knowledge and experience. But things take a long time, especially when you become wisdom, obviously. But problem is the data. Normally, we did not capture with together. So the experience left, you publish a paper, you publish a book, but data actually was not there. Because you have elevated data into knowledge, but eventually the data set is lost. So when there's a problem exists, again, it's very hard for people to repeat same process. So eventually what we've been trying to do is take the data as a source. Could be historical data, could be sensor data, also other means to compare data. You want to turn experience-based to evidence-based. But that has been continuous improving process. It's not one time. But eventually you want to avoid problems, not just solve it. And you can always add value, like a fried egg. The yolk in the middle is a product, and the egg white is a value. So we call value creation problems. So by creating the value, so from the problem, for example, you have a fuel efficiency problem for aviation, or you have a ships, but by understanding how the aviation process, you can save a fuel. It's not about engine problems, it's about fuel efficiency problems. So again, this is a very different view about what we're talking about services. Now, of course, this is a chart I use all the time. We call this a 4-quadrant thinking. Typically, we divide the problem space into visible and invisible, two types. Then we can address how to solve the problem, or we want to avoid the problems, right? And eventually, that's our goal, try to avoid problems. But typically, we start the problem solving by using our experience and continuous improvements, especially in manufacturing industry. But later on, of course, you develop a knowledge model or a product process model or SOP. You want to avoid that. So everyone can follow same discipline and to predict or to even to plan ahead, not to happen again. But that's what optimal goal for industry. But that's not enough. Like I said earlier, if you don't have a data to support that, only based on the practices, then you only have a same problems. How about those new problems? So eventually you want to find those invisible a relationship between the known problem and unknown issues, right? But that's where we see lots of correlations. A lot of relationship model can be developed, like a Bayesian belief network and etc. So the goal, of course, trying to avoid that unknown problems. Wow, that is amazing, right? So eventually the blue area is where we see the future of the smart AI and machine learning and analytics. But when you talk about industrial problems, then you need to focus on domain issues. Domain means the physical users, what's their pains, what's their issue, not about what's our algorithms work. So eventually, the typical issue for invisible issue of industrial problems, I use the 3B to generalize the issue. First, it's broken. The data are collected, right, based on different person, different time, so that's broken. They're not, of course, you could have a continuous data when the volume is too big. Obviously, people don't do that. Second, the bad, because the baseline, different collaboration, and the sensor location, or is the wrong source of data. Often there's a lot of inconsistency of the data. So how do you identify those bad data before they use it, right? First, you find a useful data. Second, you want to find out if the data are usable. So the data is bad, then you're not usable. The third, the background. Even you collect the data, label them, but the background, if you did not label properly, then later on, data cannot be used again, right? So the background is very important. So the context. So I call 3B problem: broken, bad, and background. Those are the three challenges. For example, I monitor the elevator. I don't even know what elevator what's the weight, right? I monitor the jet engine. I don't even know what type of weather. So the background information is missing. Even you know information about engine, probably doesn't help you save the fuel. So eventually, I have found some examples about how we physically been used for the last 20 years, from the broken issue, background issue, and bad data issue. Right? Let's look at three. Eventually, we look at the future smart factory issue. How the people can recognize problem in manufacturing before the problem even occur. Right? So you don't have to have alarm. Without alarm, you have more prediction. Alarm is a detection. When you have detection problem, they're already there, like end-on. When end-on happened, the line stopped already, so too late. So the 2005, we worked with Komatsu. Komatsu was one of the members, and they had a number of machines being connected, satellite. So they sent an engineer to work our center for 18 months. So this basically was saying, if when machines are connected, eventually the data are going to be collected and eventually transmit remotely, but that costs a lot of money actually. So really one of the things you want to, what's the purpose of doing that? You want to maintain the operation uptime for customers. You want to and have a long-term service support for the customers, like running time by the hour, and then you want the leasing company to able to support customers and worry-free. But to do that, obviously, so several things happen, right? First, what service computing is about. Traditionally, you send the data remotely to Japan, large data sets. Very quickly, engineer saying, well, we'll become a data company now. How can I have time to do something else? It's very difficult. So eventually, what we experienced to put a edge computing in the system and to stream the data locally in the edge side, physically, and using a computing locally to understand the potential issues and also compare them day by day. Eventually, you can predict certain kind of components before they become problems, right? That was in the locally 2007 was demonstrated, and it was very useful because you can predict each bulldozer remotely. Could be the mining side, could be oil field. But of course, that's not the purpose. The purpose is you want to worry-free users, right, to plan their productivity, performance. So eventually, Komatsu move ahead based on their dream. They want to say, hey, I'm not going to sell the product only, I want to sell services. So they start providing that kind of a drone to scale entire a construction site, understanding how many bulldozers needed, how they assign the scheduling work and dispatch the machine, help the customer can finish work in time. But again, that is kind of things. Similarly, when you work with aviation industry, have the same problems. The only difference, one's on the ground, one's in the air. So you have data from a jet engines, but a different kind of combustion temperature and the pressure, etc. But the purpose is, right, when the airline care, what do they care? They care about scheduling. They care about quick maintenance, precision maintenance. They care about no surprise. So eventually, you take a large data sets, you want to categorize them into a different cluster. For example, the green mean you want to check the performance, and the red you will do diagnostics, and the blue one you want to do a critical prediction, some safety related, right? So you categorize the data set problem first, then you do the processing. But when you have a large fleet, then you need to compare all the fleet engines to identify the weak ones. So eventually, that's a interesting way to do it. But the goal, for example, and we had involved the NASA PHM Society Data Challenge 2008. The data set was provided by NASA. The over hundreds engines was provided. So you can see this, the curve fitting based on the observation and feed curve. So you can see this roughly a curve, generalized the engine degradation. From here, basically you're trying to look at this degradation to find out for the different type of cluster units. For the most, a similar 10 units, for example. Eventually, from the 10 units, you develop called the similarity model fleet, right? You have lots of data in aviation industry, like semiconductor as well. This data set you can generalize using the curve fitting, then to the similarities to predict what it looks like. The degradation curve could be the window. So once the window is identified remains for life, you can say, well, I'm going to identify the best matches from training units, eventually rank by distance. And then we can remove those outliers, and we give a pretty close prediction. So this a challenge actually our team won #1, then still of course later on hired by aviation industry, obviously. Now the third example is a smart transportation. It's a moving on the ground, right? When you have some kind of a moving vehicles like a truck, then you have a truck. Actually, you have a tire pressure. Each a truck has 18 tire. The tire pressure quite different. Like your car and my car, the pressure level is different, but we don't even know it. Even we know it, we don't pay attention. But the truck carry a huge weight. But when you have a pressure imbalance, actually 1,000 miles, you could lose $100 of gasoline. So eventually, you want to predict that issues to look the tire, which tire is imbalanced, right? In terms of pressure, inflation. So you can quickly identify those tire and have a service done early. And that will save you time and money and also prevent potential risk, could cause some traffic issues. So then also we can predict a tire life as well. The tire life, sometimes we wait until end of a tire life, too late. But you want to retread them based on the performance acceptance level. Eventually, you maintain the tire, extend the life, right? But that's what the total value is. So if you only sell the tire, that's only a product. If you sell a tire and service platform, then you help company save money as well. But again, this is some kind of things we're talking about. So I think in general, that's what we believe is these things can help to generalize general service transformation. But of course, there are many other industries, semiconductor industries and EV industries, right? In particular, battery, etc. So those are the things. Now let's look at the industrial AI and resilient systems. How we start from there. The typical smart industrial system, like I said, regardless what product you're making, right? So basically, there are three challenges. One is the equipment level. On the product level, how can we make the product become self-aware? Self-aware means I am a product. I know what's going on. I can check myself based on degradation. The tire can self itself. The engine can check itself, right? The ship can check itself. The train can check itself. Wind turbine can check itself. But that is very important. Not just control itself. Control is done, but the condition keep changing. The multi-regime keep changing, like wind turbine. Machine's there, but the wind keep changing it. The moistures could have ice accumulate on the blades, and if you're in the mountain, all right. So eventually, when ice accumulate on the blade, that reduce the energy generation. Also, give imbalance, could cause the failure of a bearing. Now, also operation level, when you have a large number of fleets going on, you want to predict and prioritize which one should maintain, should service first, should schedule first. So therefore, optimization, right, need to be done. So because you want to keep all-time readiness. The third thing is very important. Product, normally you have to synchronize with decision making because you have a supply chain connected, right? Not just product itself. Supply chain comes from logistics. Like today, I think many people have heard about, right? The cargo is very expensive. $20,000 US, right? And you between the cargo and then you have containers and the container is very expensive. That you don't have enough ship. Once your ship arrive, you don't enough for truck. When you have a truck, then you lack of you need more containers. So now it's very imbalanced. So many now semiconductor also is a big issue. That when that's is short of is in shortage, then many vehicle cannot produce. We have heard many companies have reduced production. Today, you want to buy the new vehicle, you go to see it yourself, a dealer. They will tell you we have a low inventory. We don't have enough cars. So again, synchronize. It's not just product in the field, but also the supply chain, components, and the shipping, logistics, etc. So this is all connect system. We're not talking about service or product only, right? For customers. So eventually, resilient system really mean the system is agile. The operation system is agile to survive, right, in different unforeseen impacts, adapted to disturbance and disruption. But this is a very difficult situation because you have, especially in the global connected operations, like Foxconn's global company, we have to connect our supply chain globally, right? Resilience is one of the main qualities going to be integrated in the future services as well, because you have to look at the product and the service value, not just the product reliability use. That's a very important part of service function. So again, when you apply to maintenance in particularly, so from the reactive side, preventive side, predictive side, and you want a resilient system so that you can have for example, when wind turbine and system is become degrading, you can change, right? And different angles, the blades, and eventually allow, and also the speed, reduce the speed, allow a graceful failure. But we don't want to continue running until they reach the predicted remains for life. So you want a graceful failure until the service be performed. But again, the self-aware self-maintenance is more than just a single machine level, as they continuously benchmark with the peers. Eventually, they alert user, the operation manager, to make decisions. Now, this is a particular chart I made in 2011, published by the Annual Review and Control. Basically, is that if you look at the complexity system and the uncertainty system together, the maintenance itself comes from the condition-based maintenance field, eventually become a prognostic and health management. So PHM Society was formed in 2006. And so that was from the year 2000, it was just a condition-based maintenance. But later on, this field has grown so much. So of course, the goal is really to go beyond just a predictive, the self-maintenance and resilient system, and eventually become self-engineering immune system, right? That's the optimal goal, the future engineering system. But that's very difficult to achieve because it's not just about control itself, but also the prediction about the service support, about also the design, and about the closed loop as well. So this is one of the paper we published earlier, could have some reference as well. But let's look at how we look at the industrial smart resilient system. First, we monitor the system. Then we basically predict using a PHM prognostics. Then we have a sound RUL prediction. And in semiconductor, we often use virtual metrology. Of course, but there's many relationship between the measured outcome and also the process deviation. You want to correlate with those. So we move from virtual metrology to predictive metrology because the process updates, relationship models, right, peer-to-peer, that become very critical. So you can understand the relationship degradation, not just a physical problem degradation, right? So when you see a person with a problem, sometimes they have a relationship problem with a family, with the friends, but that you could not see, right? Human beings like that. You only see a problem. I got stress. Well, what stress come from? Untold story. But eventually, that you want to be resilient, you have to be worry-free. So industrial systems like a human, right? We have a lot of relationships. Product also relationship with environment as well, with the user conditions. So how we distinguish, how we model those changes, that's a very challenging. So the issue comes on data quality. We came from a lot of data quality issues. When we collect the system, model the system, often we say, oh, could be wind turbine, could be robots, could be machines. But we train a system, we take 20% of the data, 30% the training sets, then we validate, we test it. But again, the problem is previously we already had the problems. So first, can we detect the old problems using the same data, using the same data before we continuously collecting them? That's very important. Very often, companies collect lots of data. They don't know how useful data is, how usable they are, until they later on they found out. When they start analyzing, they say, oh, data cannot be used because some backgrounds are missing. Some background context was not labeled. Too late. So first we have to test if the data can be usable to use it to detect the old problems. Second, can be for diagnosable, right? Third, can be predictable. Eventually, we have to look at the three categories, make sure the data is useful and usable before you continuously collecting them. That practice is very important. I think today I notice a lot of researchers are crazy about algorithms and deep learning. That's a good thing, but if a domain data set had the quality problems, then it doesn't matter how good algorithms they are, the result going to be not real, right? You're going to have challenging issues. So therefore, when we define AI, is a cognitive science, right? That has been broadly used by all researchers and the people in all kinds of imaging processing, voice recognition, etc. But industrial AI is a systematic discipline. How can we systematically compare the tool, evaluate the data, and use the data, optimize the selection of a tool? Could be running the tools in parallel, right? But depend on the working regimes. And the product have multi-regimes. You may not have only one algorithm. You may have parallel algorithms working together, depending on which regime you're in, right? Like EV battery, you're running a local, you're running a highway, you're running traffic, you're cold weather. The battery life is changing all the time. The degradation will occur. One algorithm may not work. So eventually, we look at the four different challenges. One, you want a fast decision making. You want a precision of decision making, well, the system of complexity and uncertainty. So those four things give us a great constraint, select the best algorithms, right? Sometimes these algorithms, they coexist actually, right? So of course, you want a perfect speed, precision, of course, no free lunch. So we have to have some trade-off based on the selection. So if you take all the algorithms together, just simply pick a few, like you have a random forest, your logistic regression, you have deep learning supervised machines, but you compare them based on those characteristics. For example, you have a lack of training set data, you have a noisy data, etc. Which algorithm work the best, right? Of course, the data may change depending on machine running, product running different type of environments. We call multi-regimes. So those are the challenges that are going to constrain us to use the best tools to solve the right problems. So let me give some example how we implement those things in a large scale and complex system. Well, first look at the challenges of the prognostics of a complex engineering system. In general, there are four different type of category, right? They may have four altogether, like a dynamic working condition, like aviation industry, high-speed train, right? Wind turbines, typical examples. They continually changing, right? The EVs to some extent as well. You're driving and you accelerate, you stop, and you uphill, downhill, and so machine variation. Of course, the different models and different types, and very often you have different uses, applications. So different calibration processes. And data availability, yes, some machine you have enough data, some machine you don't have enough data, right? And not all machine have all data, and depend on user side. In some country you don't have data collected. Like for example, in some conditions, semiconductor environment, the data cannot be sent out, so you don't have enough data. So you have a suppliers inside the foundry. The foundry user, they want to keep data themselves. They're not going to share with anybody. So eventually, then from the supplier side, like and the CVD, PVD, and the etchers, equipment maker, and then you cannot get those data. So you have to develop your own algorithms and the service models. And knowledge availability, of course, and different generation of workforce. And people retire. Look at the semiconductor company 10 years ago until now, many people retired. Aviation industry, same thing. People retired. Now a new generation workforce coming in, you don't have enough knowledge. The model you selected, you built could be quite different. Again, so those things challenge us to deal with real world and large scale problems. So we got to rethink the fleet, because when you say large scale system in general, fleet is the issue. So what is a fleet? Fleet is a number of similar independent units. They work distributedly around the world. Or you have a fleet of machines, right? And fleet of a power system or wind turbine or EV. Again, this is just typical example. Of course, it's a one scenario, right? So another scenario could be a similar machines in different location, or in different machines similar, made by different company, but in the same location, right? So there are some methodologies in general when you apply to large scale and complex engineering system. Those we call this a fleet-based service computing algorithms methodologies. First methodology is called similarity-based. We have a large number of machines or fleets, and how you look at the similarities by comparing them to select the worst, the weak ones, rather to monitor everyone. Right. So when people are trying to monitor everyone, that's very extremely difficult and also time consuming and cost, very costly. Second thing is about fleet-based. Similarity in fleets could be different. Similarity could be small clusters, right? Fleet could be large spread, and it could be because multi-regime sometimes. The similarity base could be the same machine. I run different calibration cycles every day, right? So I can run similarities to see if a machine has any, like a train, for example. Every day in the morning, you run empty train, high-speed train, you're empty, nobody there in the morning, 2 a.m., 3 a.m. So you can see and each train sections in each different location, like in Japan, for example, high-speed train, Shinkansen. You can see the train, if any, because of the earthquake, you may have seismic movements in certain locations. You can see the train changes, vibrations. So based on that, you can check the safety concerns as well. And the methodology 3 is reference-based. We take the lots of historical data and to use as reference rather to continuously model those as well. Human being is a good reference-based animal, right? We have our memory, we use serve as a reference. Then we ask other people opinion, serve as our references. Of course, eventually that combined hybrid model make us cognitive decisions. Methodology and also the 4, and I think we have the repeat here, multi-regimes, right? Should be multi-regimes. So from machine working on multiple regimes and how you physically take different baseline. For example, semiconductor tool, they have different recipes. The same tool have different recipes in the same wafers, right? And different wafers. How you physically predict the etchers and also your PVD. And eventually you want to connect the streams when process are connected and the product connected, right? So how you physically look at the string of changes rather just a broken in the render inspection. First, let's look at an example. Let's say we have a wind farm, what we call the service, right? Company want to maintain the wind farm. You have a similarity-based low wind turbine, the wind speed, every day. So every day we do the ranking. For example, you have a cluster wind turbine. Every day we do a ranking of a high-performance turbine and a low-performance turbine, right? So we grew it into 3 clusters. When the low-performance turbine, then we look at a health indicator to find out which one is the lowest one. Then we find out those physical component-based sensors to find out what exactly the problem caused they become the lowest one. So by doing that, we have a wind farm, it could be hundreds of wind turbines. Rather to do every machine, we quickly every day I can identify lowest 3 turbines. Look at the issue, could look and depend on the level where they are, right? So this has been a patented technologies and to use for clustering techniques. It's quite useful. So we have used it for large, a quite number of wind farms and the companies and throughout the world. For wind, you can see a wind curve here, left side is a power generation versus wind speed. So when wind speed changes, of course, power generation, the curve is different in terms of but if you take a slight time machine every 1 hour or every 10 minutes, depending on how tight you want the window, you can see the power curve when distribution. So based on the power distribution of different time segment, you can generate a reference model based on the change, right? So that reference model become useful. Then use that to compare, right, which time when different wind speed, for example, certain wind speed changes, you can predict if the model is still the same. For example, if the wind speed today versus 3 days ago is similar, but the output is different, then something could be wrong. But again, we look at the deviation variance, a level, confidence level, decide. So that's the kind of things we use as a time machine-based health analysis and to decide how the maintenance and logistics should be arranged. Now, the semiconductor, similar things. You have a etching equipment, right? You have a different recipes in there. You want to trace those data, and eventually you want to monitor those processes. But of course, you have the features, a collection, feature extraction. But if you look at the patterns, the segment of segmentation of the pattern is very similar sometimes. So rather to monitor data entirely, you want to trace the segmentation. You want to look at the profile. So you can look at similarities from there. So you can quickly use that as a baseline reference model and to predict the quality we call the metrology, the yield. And from there, you can validate the process by process, recipe by recipe, cycle by cycle, right? So eventually you can decide the cleaning actions could be you want to do chamber a cleaning based on the different. You could have a similar chamber by different company suppliers. One could be by Lam, could be by Hitachi High-Tech, but you could have a similar chamber in different locations, right? You have a number of fabs you have. So eventually you can develop a good planning production system. We call it predictive metrology. So this goes beyond virtual metrology, more based on the one tool, but predictive metrology based on entire fab. Right? That is quite different. Once you have that, then I think the fab become a digital twin. Yeah, you can physically predict those wafers. Now that can go back to the tool design and the tool maintenance. Here to show the pattern-based feature for, if you look at the typical, you have a sensor pressure coming in, then you have different patterns, then you have a different work process. You have the system. Now from the segmentation, you can see a detailed segmentation. They are quite different type of patterns. They are quite repeatable. So those patterns repeatable, you can use it as a traceability, and based on traceability, and you can use that as a reference and use it as a comparison model. From here, you can predict and pretty automatic actually, as we call semi-automatic, and the success rate is very high. Rather depend on every individual, every cycle, every tool. You can use the tree segmentation and for enhanced service a performance for each different tool. Of course, if you look at the process from collection side and trace partition and feature selection and eventually and limit, how do you segment, how do you classify the problems? The process can be semi-automatic. By doing that, I can have a clear line about the limit optimization and limit management. Eventually, you can feedback loop to select better features, right? That ranking system can be continuously improved. And so this causes a systematic process. Used to be every process done by individual, and someone want to repeat, and then they're very hard to repeat. So I want to make this whole process because semi-automatic, And so eventually the process can be reusable for different tool for different users as well. For just a tool developer, of course, user side might have their own models, right? You have like Intel, TSMC, they have their own models. But again, this is challenging things, how we two things combine together, because both sides need to have something to improve the machines and the yield and the wafer yield. For example, for the multivariate limit optimization adaptation, based on those FD models, and you can use a clear a line and segmentation, and you can make decisions for line limit adaptation with the moving windows. So decision can be made based on the type of recipes and the type of a number of process has been done. So this can be adaptive rather based on traditional historic models. Okay, so methodology 5, we call stream of X. What I mean that we have a large number of factories globally around the world. So how we manage in each factory, obviously, each factory has machines, right? With physical manufacturing processes. So we want the machine can be monitored, but the data can be generated from each process check. So basically the cyber side can be one site. Physical site could be many sites. So we could have a one data analytic center locations, monitor hundreds of factories around the world, but those analytical foundation platform and to serve as stream of X. For example, the quality at each process, like SMT, surface mount, right? Or could be continuous a manufacturing process. It could be a different type of connected systems. You could have energy problems. You could have a quality problems. So stream of X, stream of quality, stream of energy, stream of what? So for example, in Foxconn group, there are 175,000 machine tools and 80,000 robots and over 1,800 SMT line globally, right? Which is about over 10% the world capacity. Now, if you look at this, a large number of manufacturing, right? One time Foxconn worker exceed 1 million employees. Now we have about 800 something. So, but again, when you have a connected system together, that gives you a richness of the data, but not on the edge side. You need to have a good service computing algorithm to streamline, to correlate, and to label, and to cluster, so that in the cloud side, I can do easy computing based on fleet-based approach, rather based on the individual machines, because the data volume is too big. So this is one of the approaches we've been using, and because the company started an industrial internet companies in 2018 as a service function, not just a manufacturing company. So this the factory, for example, received 2019 World Economic Forum Lighthouse Factory Award. If you Google WEF Lighthouse Factory, you'll see that this is the best in class in terms of Industry 4.0 manufacturing, right? So which means you have to have an end-to-end in solutions and also the efficiency management. From here, you can see the labor reduction, 92%. What that mean? It means, oh, you reduce a lot of people. Not really. It's you reduce redundant labors. Why? If you go to factory today, you see people very busy. Look the end-on, look the breakdown machine. They're running around like chicken without a head. And then they worry, every machine, they worry about the process, they worry about quality. So they're firefighting every day, right? That's what today's manufacturing. Now, if you turn off the lights, you don't have to run around. You only go to the machine precisely when the problem not happening yet, but it's going to happen. So we call lights out factory. So we did this to challenge our own people, not to worry about manufacturing quality, rather to predict degradation. So this become well-known, our symbol of in the Foxconn right now. So of course, people may say, oh, I can turn off the lights myself. That's not a saying. We truly use it as a challenging tool. So this year, again, another site received the second Lighthouse Award among 60. So far, there's over 69 Lighthouse factories, and I think this year again we have another several sites select again, which to be announced soon. It could be next month. But internally we're going to build 20 lighthouses site within Foxconn this year. So we mean these kind of practices give us people worry-free. So again, when we have a service value, I mean really employees productivity ups, and also the customer value ups, right? That's what we're talking about. Now let's talk about Foxconn stream of quality methodology. So when you have a process connected, right, then you have local materials and machine and method environment changes. But when you connect it, so how these connected quality become a system, right? So we used to have a individual quality at the inspection site, but they're not connected. If they're connected, then you don't have a blockchain driven kind of a non-erasable credibility. So what we want to do, we want to label the process on each site, each time window. So eventually the stream of quality is become a systematic methodology for connected quality. So by doing that, you can see that, so for example, you have a manufacturing processes based on inspection you have, and you have a data first cluster based on different types, and you can segment based on different in the a working regime. Then you can decompose them based on different problems. Then you can analyze them based on a different type of issues. You can predict them. Then you share with a different level of a management. It could be operation, could be maintenance, could be the a customer interface and the CRM. Then eventually you want to keep a customer worry-free and our operation worry-free. So the stream of quality is a methodology that deal with a large number of connected processes and systems. EV is extreme of health, same thing, because they are connected, right? And the battery life cycle is connected. And so eventually how you drive, it become very challenging. So again, let's look at the next generation. After we have all the things, what can we see the next? Well, architecture, very important. Of course, we can do try and error. Everyone can develop their own vision or dream, but realistically, as engineering, we need architecture, right? So architecture means somehow you need to have a systematical approach so people can follow, people can challenge, and people can improve, rather just compare for different apples and oranges. So here we present you a cyber-physical architecture for a industrial relevant system, right? So in the low level, it's a physical connection, could be an MT Connect, could be in the OPC-UA, and it could be different standard depending in the different countries. And the second level is the edge side, where you put the edge computing or service computing in the edge. The third level is cyber side. Cyber side means you connect to the multi-locations through the cloud, where you can generate a physical model and a data model, cyber model we call, together. Then the fourth level is a cognition model, how different people see different results, right? And just different people see different results. And that's what the purpose, and how to present the thing to people. Eventually, how to take action to make changes and decision at different time for different purpose and different locations. So the 5C we call the connection, conversion, cyber, cognition, and configurations. So by doing that, obviously, these first two layers is the local side, physical side. The upper three layers is about the cyber side, right? So the cloud is the middle, which provide a platform, allow the connecting physical and the future digital space. It doesn't matter, it's factory, it's and the wind turbines and the subway, whatever. You can do similar things. So by doing that, obviously you have a data analytics on the edge side. And once you go into cyberspace, you start using the data as a platform, right? And eventually you have a first closed loop feedback to user. Then you have a self-management function, allow something you don't see physically, but you see now by comparing. For example, you drive the car, you have no idea what battery is. Now, after you finish the car, I can show you how the battery is being used based on your driving behavior, right? And so day after day, 2 years, I can see that you have a degradation about 5%, 10%. Wintertime, you drop to 12%, etc. So that's a very visible from the user side now.
Dr. Lee, could you wrap up in maybe 5 minutes?
Yes, I will.
Thank you.
So eventually, you have a system that the left side is a physical machine, and the right side is a cyber machine. So when machines are connected, right? So the location, physical side data can be extracted. Eventually, the cyber side thing can be correlated based on the time window and time window based time machine, so that they recognize the variation locations and time, and they cluster them together in different space, so that a cluster become very useful. It can retrievable in the future, right? So the end of life product, you can trace back what happened in the past. So this is truly is like a avatar, that kind of things. So in the end, so this is when you apply to large scale system, not single machine, like a high-speed train. You have many components, like you have a motor, your bearings, and etc. So just quickly show you, once you connect these things together, then the entire system can be become a system of large fleet, right? Large fleet can be connected. Then each machines, you have a bogies, and then you have a motors, you have a bearings. Then they compare them section by sections, and train number by train numbers. Eventually compare which one is degrading the most, so they can optimize locations. Eventually find out where's problems, which one should be maintained first. So based on that, you can rank them. So this has been done by different companies, including Alstom in France. Conclusion. I think to conclude, when you look at service computing in the industrial AI, we call the use A, B, C, D, E. A is analytics technology. We call algorithm based. B is called big data. It's the data generated, doesn't matter historical records or sensor or fleet. C is a cloud or cyber, the platform to support service computing. And D is very important, it's a domain know-how. You cannot just run data without knowing the domain problems. The industrial environment domain is a king. Of course, the results, evidence. The customer only care about the evidence. You can code great algorithm if they cannot save money, if they cannot make money, they don't care. So D and E are most important in industrial AI space. Of course, it depends on the application, but most likely the ABC are the fundamentals, and we need to drive more D and E. There's a book I published last year called Industrial AI by Springer. Obviously, it can be used as a reference. Again, thank you very much for the opportunity, and you can see some more publication from Google Scholar and ResearchGate. Appreciate it. Thank you.
Thank you. Very exciting presentation, and certainly broaden our view how industry try to migrate AI technology to all aspects. Not like we are doing focus on research, focus on very in-depth problem, and try to make a breakthrough. But industry problems certainly is very broad and a very wide version, and also dynamic. And thank you very much for Jay, with your experience, your current position, and also the top management area. Certainly you give us a very broad view. Thank you very much.
Appreciate
it. Any question come up? If not, I have some comment and a question.
Okay.
Carl, any people, any question from the audience? Carl?
I have not received question yet.
Okay, then let me continue.
Okay.
When you talk about the industry artificial intelligence, eventually your domain or your direction is much broader than what we usually talk about deep research problem. Okay, so research problem, as we all know, in order to have a very focused study, we establish a model. And in your talk, you already talked about various model. And of course, the first stage, the first challenge to deal with industry is how to build up, how to conceptually come up a workable model that you can extract the characteristics, then focus on use with all the powerful mathematical or AI technology and to solve the specific problem, and also get the feedback. Can you shed some light? I think
Yes.
the first stage is the most challenging.
Sure, sure. Okay, thank you for the question. I think it's a very, very good one. And so let's first look at the model, right? And there are three different types. First is a developer model. For example, I'm a company. I make wind turbine. I make a high-speed train. I make a machine, right? So that model, I have it because I designed it, right? So when someone bought my products remotely, I can connect the product. I can do troubleshoot, right? That's why the dealer have a computer to do onboard diagnostics for you, right?
Yeah.
But the problem is, and user also has a model.
Mm-hmm.
For example, I'm a company. I use a different type of products. The good examples are like a semiconductor, right? You have a different suppliers like Applied Materials, Lam, Hitachi High-Tech, and different companies. Now you have a user like Intel, TSMC, and Samsung, etc. So they have their own models, right?
Mm-hmm.
They're not going to depend on only one company model. So hey, I'm going to have my own model, right? My model means I'm going to optimize my process because I know the recipe I'm using, and the product side, they don't know my recipe, right? So that's the second thing, the code data model and the process model. The third type is called the system service provider model.
Mm-hmm.
Very often, service provider could be a third party, for example, like an elevator, right? Like many other different the company product could be a third after warranty period, be a third party.
Yeah.
The third party, they have a domain knowledge of the field. They may not have a product domain design. They may not have a user site, but they don't know how you drove the car. They don't know how to design the car, but they know what the problems most likely happen based on 100 cars you repair, right? So they also know which component lasts longer than other. So the product developer model, user model, and a service provider model. There are three different things, but they could be integrated together.
Yeah.
Right. So that's where I believe service computing has a much bigger growth space because it's not just about the developer and the field services altogether.
Yes. Very good. Okay, I have another aspect, which
Sure.
you already mentioned. That is the data. Okay, if we just have the model that's based on the perception and our domain knowledge and what things should be doing, but really try to tie the real world, the practical problem, we must have good data. Yes. And the data, as you already mentioned, there's so much data, and we need the important information from the data. It's what's called smart data. The data is really directly related to the problem or the trouble the manufacturer or the industry people see, how to improve their product. That's the key thing.
Yes, yes.
As you already know, that a big data, smart data is a very growing research area. Okay, but how we tie how can we systematically to tie the data with the model in the early stage, and continue update.
Sure.
So that when you use the model, you get the updated data and the smart data for the current situation and with the good prediction for the future.
Yes. Well, again, Steve, you're asking very good questions, right? Because this is the data quality and data usefulness and data richness, also the key issues. So typically, I call this a three data quality evaluation platform. So we look at the two different levels. One is first, I'm a user, and always have problems. Now you have to find out which data are useful because there are so many data, right?
Yeah.
So first, you divide into another space. One's a frequency of problem. Another axis is called the a significance of a problems. For example, I'm running a wind farm. I'm running a high-speed train. I'm running aviation. I'm running a semiconductor. I'm running a EV system. So frequent problems, frequency versus a criticality, impact level, right? So then they have four quadrants. High frequency, high impact. Oh, that's a no-no. You must solve it. It's very useful. Once you have that, you must do right away, right?
Yeah.
And high frequency, low impact. Well, you can have some data. You find out more relationship. And the low frequency, high impact, it doesn't happen too often. Once it happens, it shut down.
Mm-hmm.
Oh, that's very important. You need a predictive model. And low frequency, low impact, you probably should live as it is, right? So first, you look at those distribution and quickly find out which data are useful based on historical system. Then second level, because usable. Useful data may not be useful. For example, food. Fish is useful for our anatomy. But if a fish raised in the dirty water, it's not edible.
Yeah.
Right? Our blood is useful. But if I donate blood with hepatitis B, that's not usable.
Yeah.
So now how do you know data usable?
Yeah.
Well, first, I have to evaluate from data are collected. I'm start evaluating based on the repeatability. The first day, of course, impossible. After one day goes by, every day I compare, right? I look at a reference. For example, the machine run a dry run every day. Like a high-speed train, they run every day. Every morning they run dry run, empty train. Why? Because they build baseline models.
Yeah.
So eventually, over time, you build a good reference model, right?
Mm-hmm.
Yeah. So then if you find some data is not usable, then you start re-engineer to maybe add more sensors, or if you feel data too redundant, you may eliminate some sensors. Eventually, you need the right sensors, the right data for the right things. Yeah.
Mm-hmm. Very good. Yeah. Well, certainly there are a lot of...
Just one more question. One question from the audience.
Okay, go ahead.
This is from Gogan. Thank you for this presentation. My concern is about how, with these new technologies and models, to consider, meet and align the business plan and the enterprise strategies with respect also to the security and privacy challenges with the quantity of data treated today.
This is a very timely issue. Also, always have been an issue, especially the privacy and also the security issues. And of course, when we develop any systems, right, we have to address the weakness of any system. Now, there are different methods being placed. For example, we use called the federated learning system. When we start sending using connect systems, we don't normally send the send the data out. Sometimes we only send the process model, send the key parameters out to fit the model in the cloud. And so there's of course a different approach you can do. But again, when you have new methods, first you need three things to support that. Number one, you need to support the baseline. The baseline system has to be reused as a reference. Second is called the bottom line. The bottom line is security, right? The cost and downtime, whatever people say the bottom line. So the bottom line means it doesn't matter how good technologies are, you must meet the bottom line, right? The third is called the best line. The best line means how much you improve, 2x, 1x, 3x, right? So, but if you can meet the bottom line and baseline, you have 1x, then you can do continuous improvements. If you can meet the bottom line, but you cannot meet the baseline, you meet the baseline, but you cannot meet the bottom line, It doesn't matter 3x, probably people will not use it, right? So this is we call the 3B: bottom line, baseline, and best line. Yeah. So that's very important to combine together.
Very good. Thank you.
Thank you.
Carl, more question? Carl?
No, not at this moment.
Okay. All right. Well, I think our time almost up. And
Okay.
before we finish, and I'd like to make a announcement that this Friday, today is Wednesday, okay? Friday, we have a plenary panel session. The topic is future trend of strategy advances in service computing using AI technology. Well, very closely related to this keynote and also a couple other keynotes at this conference. And JD, thank for him. He also is one of the panelists for that panel. And hope you can attend. And certainly, I thank the keynote speaker. JD gave a very exciting keynote, and also all the audience coming and participate in the discussion. Very good. So I think our time up because I understand only 10-minute break. The next session will start. So we cannot extend too long. All right. So thank you. We close this session. Carl, do you have anything to add?
No, thank you. The time is just about right.
Okay.
Thank you very much. Yeah.
All right. Okay. See you. Bye.
Yeah. Thank you, Steve, for sharing a session. Thank Carl for the support and Ella.
Yeah.
Okay. Bye-bye.
Okay. Bye.